Hello, Advanced Geometry students. It's Mr. Donaldson. We're going to do section 9.2 notes today. It'll be broken into a couple of sections. First, we will review the Pythagorean theorem. Then we'll talk about the converse of the Pythagorean theorem. And then finally, we'll talk about a type of problem I'm going to ask you to do a few times this unit, and that is called a Pythagorean system. So the first thing we'll do is we'll review the Pythagorean theorem, and we'll do that with a problem like this one that will involve a quadratic that we'll need to factor. So first, to set up the Pythagorean theorem, we're going to do a squared plus b squared equals c squared. And of course, we want our c to be the longest side there, the hypotenuse, I should say. So we got x squared plus x plus 2 squared equals 10 squared. All right? Now, when I square this binomial, you got to make sure that you FOIL it or distribute it. And so I'm going to just show my work and write it like this. Because when you square something, it means to multiply by itself. So I'm just going to show that. Of course, if you could do this part in your head, squaring that binomial, that's totally fine. So I get x squared plus, this is x squared plus 2x plus 2x, which would be 4x, plus 4. And that would equal 100. Now, because I have a quadratic, I know that I'm going to get everything set equal to 0 on one side, and we're going to factor. But first, I'm going to combine my like terms and get it set equal to 0. So x squared and x squared is 2x squared plus 4x. And when I subtract 100 from both sides, I get negative 96, and that is equal to 0. Now, right now, factoring this with a leading coefficient of 2 is kind of a pain in the butt, but I notice that every single one of these terms is divisible by 2, which makes it actually an easy factoring problem. That would give me x squared plus 2x minus 48 is equal to 0. So now when I factor, I get x and x, of course, and then I just need two numbers that multiply to negative 48 and add to positive 2. Well, that's going to be positive 8 and negative 6. Which then, by using the zero product property, would give me two solutions of negative 8 or 6. And then, of course, because this is geometry class, we need to go back and we need to make sure those answers make sense. And you'll notice that x represents a side length, and so therefore it cannot be negative, so I know negative 8 is not a viable answer. So x is 6. And you could always check this as well. That'd be 6, that'd be 8. That would be 10, and 6 squared plus 8 squared does in fact equal 10 squared. 100 equals 100. There you have it, my friend. So just a little review of the Pythagorean theorem and the types of problems I'll ask you to solve. They're going to be a little more complicated sometimes than just solving for a numeric sideline. All right, the next part of today's lesson is focusing on what are called Pythagorean triples. Remember last chapter, in chapter 8, I stressed how important it was for you to memorize the formulas? Well, I'm going to stress to you today the importance of memorizing your Pythagorean triples. And the reason these are so important is that these are going to show up frequently, and if you have them memorized and you know them, it's going to make your life substantially easier. All right? So, Pythagorean triples are essentially three positive integers that satisfy the Pythagorean theorem. For example, 8, 15, 17 is a Pythagorean triple, because 8 squared plus 15 squared does equal 17 squared. So it's just integer values that satisfy the Pythagorean theorem. One really important thing to understand, of course, is that the biggest number must be c, that must be your hypotenuse. So what I have here in this top row, these are the most common Pythagorean triples. A 3, 4, 5, a 5, 12, 13, a 7, 24, 25, and an 8, 15, 17. In the subsequent rows beneath the top row, all I've done is I've taken each one of those Pythagorean triples and multiplied them by the same factor. So for instance, if 3, 4, 5 is a Pythagorean triple, well, I can double those numbers, and that means that 6, 8, 10 is also going to be a Pythagorean triple. So the goal here is you memorize this top row, and then if you could just multiply those triples by some number, that will also have to yield a triple. So like if 5, 12, 13 is a Pythagorean triple, then I double those. 10, 24, 26 is also a Pythagorean triple. So again, the goal, memorize that top row. Memorize those four basic Pythagorean triples and just know multiples of those will yield Pythagorean triples as well. And the reason this is so helpful is look at the example 1 here. All right? Without having to do any work, I can tell you that that missing side length is 4. Because 3, 4, 5 is a Pythagorean triple. So if I have one leg of 3 and a hypotenuse of 5, 4 has to be the other leg's length. So notice how quickly I can solve these problems because I know my triples. The next one, 10, 24, something. Well, this is just a 5, 12, 13, but times 2. So 10, 24, 26. So if one leg is 10, the other is 24, the hypotenuse must be 26. So if you have these memorized, you all, you're going to be able to rip through some of these right triangle problems really fast. One thing to look out for, though, of course, is you may see something like example 3, where you'll notice that 8, 15, 17 is a Pythagorean triple, but in order for it to work, the 17 has to be the hypotenuse. It's got to be the longest side, and in this case, you would probably try to put the 17 there, but that is not possible. So in this case, it is not a Pythagorean triple. Now, of course, you could just set up the Pythagorean theorem and you could solve for that side length, but the purpose of these problems is to use triples and to demonstrate to you to be careful and make sure the longest side is the hypotenuse. All right, we'll use these throughout the unit, and I'll try to reiterate the importance as we go. All right, so finally today, the meat of today's lesson is the converse of the Pythagorean theorem. And the converse of the Pythagorean theorem just works backwards from what we did in section 9.1. The Pythagorean theorem simply said that if you have a right triangle, then the side lengths must satisfy a squared plus b squared equals c squared, where c is the hypotenuse. So today we're going to say, hey, I'll give you 3 side lengths, and then I want you to tell me, is that triangle a right triangle? And what would make it a right triangle will be if a squared plus b squared equals c squared, then it must be a right triangle. All right? So in doing this, you all, it is important, of course, that you determine which side would need to be C. Now remember, C represents the hypotenuse, and the hypotenuse of a triangle is always going to be the longest side. So the goal here is to establish and see, is C squared equal to A squared plus B squared? So I put that box there in the middle because I don't know if it's equal, and I'm going to try to figure that out right now. Now, in order to ensure that C is the longest side, one trick that's helpful is to first, because I'm going to square all these anyway, if I square all these, the biggest square would have had to have been the biggest side length. So I'm going to square 5 and get 25. I'm going to square 5 root 5, and 5 root 5 squared is 5 squared is 25, times root 5 squared is 5, so that's 125. And then 10 squared, of course, is 100. So you'll notice that this is the biggest square. So this must be C squared. Not C, because I've already squared it. That would be C squared. Then I'll call this A squared, and I'll call this B squared. And now I'll go over here and I'll say, okay, I know C squared was 125. I don't know the relationship yet. I know A squared was 25, and I know B squared was 100. And check it out. 125 is in fact equal to 125. So in this case, because C squared was equal to A squared plus B squared, I do have a right triangle. Yes, this is a right triangle. All right, so we can elaborate on this a little bit as well. So notice my little nerd program here, and I hope you can see, I know the font's a little bit small. Maybe I can make that bigger real quick. Let's see. Bear with me here. Maybe a little bit bigger. All right. So what we notice right now, I have a right triangle. You can see that because you have the little right angle here. And you can see that C squared is equal to A squared plus B squared. Now what I want to do is I want to make this triangle obtuse. And the way I'm going to make this obtuse is by making this right angle larger. So I'm going to drag A to the left here. And when I drag this segment to the left, I make this angle larger, which makes an obtuse triangle. And what you'll notice now in this case is that C squared is now greater than A squared plus B squared. So for an obtuse triangle, C squared is greater than A squared plus B squared. Now if I drag this segment that's A back to the right, this vertex, and make it an acute triangle, now I notice that C squared is less than A squared plus B squared. 47.36 is less and 61.46. And I know this, oh, excuse me, never mind. All right, so here we go. Let's take a look at a couple of examples here. But before we do that, let's write in our notes that if c squared is equal to a squared plus b squared, you have a right triangle. If c squared is greater than a squared plus b squared, you have an obtuse triangle. And if c squared is less than a squared plus b squared, then you have an acute triangle. And we'll just practice this now. All right, so I've got 3 examples here. And the way I'm going to do this every time is going to be really consistent. The first thing I'm going to do always is I'm going to square everything and then determine which of the squares is biggest, and that will be c squared. So first, I'm going to square each number. Of course, it's pretty obvious you all 9 is the biggest of all these, but I just want to be really consistent with how I do this because when you get to an example like 3, it's not as obvious which side length is the biggest. So 6 squared is 36. 7 squared is 49, and 9 squared is 81. So I can tell of all those squares, this is the biggest, so that's going to be my c squared. And then I'll call this a squared and b squared. So, c squared is 81. How does it relate to a squared plus b squared? Well, 81, and then 36 plus 49 is 85. Well, 81 is less than 85. So c squared is less than a squared plus b squared. So this is an acute triangle. For problem number 2, this one is a gotcha. I tricked you. I'm not going to do any work. This is not a triangle. It can't possibly be right, obtuse, or acute because it's not even a triangle. Remember what we learned earlier in our class is that in order to have a triangle, any 2 side lengths need to add up and be greater than the third. But look, 3 plus 6 is equal to 9, not greater than. So if I tried to make a triangle and that was 9, the 6 and the 3 would never touch each other to make a triangle until they lay flat on the ground. So this one is not a triangle. Pay attention to that. I might try to trick you sometime. All right, so let's look at one that's a bit more complicated than number 3. So first, I'm going to square each of these. So 5 root 2 squared is 5 squared is 25 times root 2 squared is 2 is 50. So I'm squaring each of these. All right? 2 root 7 squared. 2 squared is 4. Root 7 squared is 7. That's 28. 2 root 5 squared. 2 squared is 4. Root 5 squared is 5. That is 20. All right? So in this situation, this is my c squared. So c squared, and then I'll call this one a squared and b squared. So here we go. How does 50 relate to 20 plus 28? Well, 50 is greater than 48. So I've got that c squared is greater than a squared plus b squared, which makes this one an obtuse triangle. And then the final example here, we'll do the same thing first. We'll square each of these to determine which one is the biggest for my c squared. 1 squared, of course, is 1. 2 squared is 4. And root 3 squared is 3. So 4 is going to be my c squared. I'll call 1 a squared, and I'll call 3 b squared. Then I'll set it up. So how does c squared relate to a squared plus b squared? Well, I know that c squared is 4, and it's going to be equal to 1 plus 3. So because 4 is equal to 4, I've got a right triangle. The one really important thing you all I would say with this is when you're setting this up, make sure you set it up in this way so that c squared is on the left and a squared plus b squared is on the right. It just makes it more intuitive that greater than yields an obtuse triangle and less than yields an acute triangle. So there you have it. That's the converse of the Pythagorean theorem. Now for the last example, I made a second video about a Pythagorean system, so it's really easy for you to access and practice this. So please take a look at the next video for the next example on the note sheet.